Good afternoon, participants, to the third session of the second day, FDP on 3D printing and design. We have with us in this session Dr. C.P. Paul from Laser Additive Manufacturing Lab, RRCAT Indore. So, Dr. Paul is currently heading Laser Additive Manufacturing Laboratory at RRCAT Indore. He is also Dean Student Affairs at Homi Bhabha National Institute, a University of Department of Atomic Energy, Government of India at RRCAT. Prior to joining RRCAT, he graduated in mechanical engineering from Vikram University, Ujjain. He has worked for two professionally managed public companies as a design engineer. He earned his PhD degree in mechanical engineering on laser additive manufacturing of laser Paul, sir, if you
Hello. Yeah. Hello.
Yes, sir. You are audible. Yes.
Yeah, I'm audible. Right. So thank you very much. Sorry for the delay because of the technical glitch. And now more or less we are through, and now I should be able to talk to you and present the things in different perspective. Whatever we had been doing in last 15 years and how the things are being done at the global level. This is all we'll be going to discuss all about. So I understand all you guys are, very much keen to look into it and work on this. Thank you, Yogesh, for introducing me and giving me an opportunity to discuss about what are we doing and the knowledge we have earned during the period in last 15 years. So there is small change in the title. But content remains the same. The title is now Laser Additive Manufacturing Technology Challenges and Opportunities. This is my team. You see, we have some 16 employees and 5 PhD students. All are working on the different aspects of laser additive manufacturing at Raja Ramanna Center for Advanced Technology, Indore. We'll start the presentation with the introduction. We'll be talking of global and Indian scenario. I'll also be talking about what RRCAT is doing, what are the technology challenges, and what are the new opportunities we have. And then we'll conclude the session. So what I want to is, whenever we are talking on these aspects, let's try to understand why this is needed, how these things are changing the world, and why additive manufacturing is being pushed so hard across the globe. Take care of the. So we'll be all these discussing and different. I understand we had really stalwart like Dr. Chandrasekhar and then Dr. Ravi Kumar. They all have presented in the best. And let's see how the things are different and what are the things there for you to take away this afternoon from our presentation, from my presentation. Whatever I'm talking today with you guys are basically taken from these 3 books. One is Laser in Manufacturing. Paulo Devim has edited this book, and we have our first chapter into this book. So this is a big part of this is taken from here. Another book we are going to refer on this is Additive Manufacturing Application Innovation. Again, it is edited by Professor Rupinder Singh and Dr. Jay Paulo Devim. In this, we have written chapter 2. And after writing almost 15-16 chapters in the area of metal additive manufacturing, we propose to start with this on the invitation of McGraw-Hill's Education to write a textbook on additive manufacturing principle, technologies, and future trends. So this book is in the press and likely to be released in April 2021. So this book will cover all the aspects what we need to have as an advanced course for the UG and PG level, as well as it will also work as a handbook or maybe ready reference book for the people who are working in this profession. So let me start my talk with the introduction of laser additive manufacturing. See, in full presentation you might have seen laser additive manufacturing as process of joining material starting from 3D model data, layer by layer build-up approach, and which cannot be classified as subtractive manufacturing methodology, or it is not also formative manufacturing methodology. So what we have to see, the definition which is defined in ISO 52900 defines 5 specialized criteria for a process to be called additive manufacturing. So we should focus on these 5 criteria. The first criteria is process of joining the materials. Second, it starts from 3D model data. It should be a layer built up approach. It should not be classified as manufacturing methodology, and it should not be a manufacturing methodology. So these are the 5 criteria. Now, what is happening in laser as a heat source to join the material, then it is called laser additive manufacturing. So this is the definition, and this is the thing, how things are classified and how things has to be understood clearly. Now, when we talk of additive manufacturing, you might have heard so many speakers and talking in different ways. I will say additive manufacturing is a more nature's way of growth. You see, you take a seed and how does it grows to a plant? You see that it collects all the things from the surroundings and grows. Similarly, if you talk of infant becoming an adult, it is also taking, eating and, doing so many things, and finally becomes adult. And this is a sort of additive manufacturing. We also, as a human being, try to work on and learn this technique a lot from the beginning, and they try to make the houses. You see, this is the very fantastic example. This is a fantastic example you see here. We use some basic blocks and make the house. So this is out of laser additive manufacturing, though it cannot be classified 100% as additive manufacturing. But as far as the approach is concerned, we can say this is the additive manufacturing process. So what I want to say, till today, we were not emphasizing on additive manufacturing, not because this was altogether a very new stuff, but we were not addressing this because we were not having capability to address this. This was a more natural. Therefore, we were going for some other method which were logically simple and easier for human beings to work on. Therefore, we were focusing on subtractive and additive manufacturing processes. Now, if you compare these 3 technologies, you see in additive manufacturing, I'll be highlighting some of the points. You see in additive manufacturing, when you talk of this, you see the surface finish and dimensional accuracy. You get from low to medium in additive manufacturing, while these things are pretty good in subtractive and formative. Similarly, if you talk of size of the components, a bigger component can be machined, but again in additive we have a limitation of the machine size, so there are issues. But now what makes it different? The difference comes, it uses a shapeless material and makes the thing into different form, and buy to fly ratio means what the material you buy and what the material it uses as a surf is very close to 1. So that is the thing very good. And if you talk the geometry, so it's made altogether different for manufacturing, and it is changing the whole. So with this small discussion, let's go ahead and see how does it behave for the cost aspect. In additive manufacturing, cost per part doesn't varies a lot. There is small variation. You see there is a slope, and just because of some charges like initial design charges or procurement charges or stuff which may not be affecting a lot, but there is a small slope is there because in additive manufacturing. But in subtractive and formative, as the number of parts increases, the price goes drastically down. So this is the basic difference in terms of price. Now let me introduce, when we talk of such a big technology, why do we need this? How the things has to be done? Let me take an example from a very commercial market. We all love cars as a mechanical engineers. Yes, we all know cars. Now let's take the example from a car market. Today we have a cutthroat competition. If you compare some 20 or 25 years back, we have only two companies in India who were selling the car. That is Fiat and Ambassador. So what was happening? These companies, they were targeting to this particular segment, and there was no competition. They were selling the way they wanted. So there was not a lot of change in this. Now, if you talk about in pure engineering terms, the cost of the cars will have two costs into it. One is the cost for the manufacturing that product, and second, the cost which is associated with the development part of the product. So these will be, I'm not talking of the profit and economics and other stuff. Let's talk of the straight engineering stuff. The car cost of the car will have two major aspects. One is manufacturing cost of the car, that includes the material and everything, and another part is coming from the development cost of this. Now, what is happening in these years? Though the market has grown up, but the number of competitors in the markets are also increased. You see, today we have Suzuki, we have Fiat, we have Honda, we have Hyundai, we have MG, so many players, and everybody is coming with more number of models targeting a different segment in the market. So what is happening? If you see, eventually, what is happening? Though the market has increased, the size of the size of the market is increased, but effective volume of the car sold for particular model is reduced. This is happening, and since it is reduced, the development cost is likely to go up. This is the one aspect that we have to understand. So market has gone up, but of cars sold for the particular model is reduced, and as a result, the development cost is going up and up. Another point we have to see this aspect is now the life of the car may be of 3 years or 4 years for the particular model. After that, it is very difficult to sold out. You have to either go for the facelift or some change in the technology. So maximum model you can have, maximum duration you can sell that car with the same features, everything same, maybe for 3 years. So what is happening? This is also limiting yourself. So as a result, the cost and the in money that you are investing for the development of the car is going up and up. This is the problem. Second aspect, if you see, today, people are smart enough. They are trying different effects and pushing this to help and co-op with the adverse duty conditions. This is making the difference. See, we all know that in Carnot cycle, if there is a large difference between the temperature of sinks and source, the efficiency of the Carnot efficiency will be very high. We all know that. So what is happening? We cannot change the temperature of the sink because it is always atmosphere. So best is you can always go and increase the temperature of the source. And when we talk of increasing the temperature of the source, means you are exposing your material to higher and higher and adverse duty conditions. So these are the issues. So, once you are, this is a challenge for engineers to work on. And so the most important point is, very often, a smart guy sitting anywhere in the world comes with a novel idea and change everything. And it is seen that there is a 65% success rate for the new product with the superior technology is coming to the market. So what I want to say is there is a lot of challenge for the people to work on, discuss this, and we are challenged differently. Now, if we talk of the customer end, in the customer end, people want the delivery immediately. They want good product. They want, everything should be checked robust. And the feature if we talk of, they want everything in that, whatever possible. So expectations are a lot from the customer side. So now issue is how to resolve these issues. One of the basic idea of resolving this idea, this problem is deliver the product at the best possible feature at the lowest price. It has to be the best. So best quality product with maximum possible feature, immediate delivery at the lowest price. It's contradictory. So this is the thing. People started working on different and progress. Let's understand how the things can be made. So when I am talking of these challenges, you keep it in your mind. We'll be addressing in the second part of this as we grow ahead and try to understand how the things are. So let's focus on the overall methodology of laser additive manufacturing in this first. See what is happening in laser additive manufacturing. We are starting with a model, and this model can be coming out of a object and imaging systems, or it can be the output of a designer and 3D CAD software, or it can be output of mathematical data analysis. So this will be there. And when this is done, we are slicing this model. And after that, we are doing some job manipulation. We are doing the layer by layer material deposition. And finally, your product is converted into this. So this is a overall methodology when we talk of the lasers additive manufacturing. So this is the stuff. So now when we talk of this, I told you key this methodology we are working on this aspect of it. There are challenges in the market, we have to go up with this. Now, how can we use laser additive manufacturing to change the economics? How can you take the advantage so that we can be attractive in this? I'm presenting you a conventional manufacturing cycle. So let's see how does a conventional manufacturing cycle works. We go for the synthesis of the design. We do the analysis, we prepare documentation and drawing. After that, we plan how to go ahead. Once the design and everything is finalized, we procure the raw material, we go for the tool procurement, we go for the programming and manufacturing, then we go for the quality control and then packing and usage. So this is a typical cycle how a conventional manufacturing works in the different level of design, production and application. So this is the typical stuff. Now, if you take a additive manufacturing, laser additive manufacturing, you see there are so many things which are redundant and removed from the development cycle. See what is happening? See, we are working with a 3D model. So we need not to go for a separate preparation of drawing and documentation. See, the model itself is having all the information. We need not to worry about so much. Second part is we are using laser additive manufacturing. We as a machine, we are planning whole stuff into it. So we need not to worry a lot about the planning aspect. In conventional process, we think whether this job has to go for lathe or it has to go for milling machine, or should we send it to the fabrication shop for the welding. All this planning, if it is design is ready, you can just proceed ahead. Now I'm talking of the raw material procurement. See, the moment you decide to make a product, right away initiate the material procurement. This is because what is happening, what the material it's not going to change. It is not going to change the material as far as the chemical composition is concerned. For example, if you want to make a laser piston block, you may be using either cast iron or maybe the aluminum alloy. So material is fixed. So you are not too much bothered. But in case of conventional manufacturing, unless design is freeze, you cannot go for the procurement of the raw material. Obviously, the reason is, if you think that size of the component, of the final component, which is likely to come as a design as a 200 by 200 and 200 millimeters, and because of some reason 1 millimeter goes up, you are gone. So raw material procurement, it is giving a very much lead when you go for a laser additive manufacturing. In all these applications, we are using laser as a tool. So we need not to worry about any other tooling procurement. So these are the 4 stages, 4 steps that either reduce a lot or removed a lot. So these things are changing. As a result, your development cycle is going rapidly. It's changing whole scenario. Things are making it, and saving the time, bringing product into the market early gives a very nice lead. If you talk to any business administration fellow, he will say yes, or some entrepreneur, he'll say, if I come 6 months early in the market, I can go with the product, I can have some premium of say 10 or 20%, and I can make the money. The moment other competitors comes to the market, I can push the price down and throw all other competitors out of the race.
Sound zero K.
Hello. Yeah.
Yes, sir. Please continue.
Yeah. So that is the thing which is changing the whole scenario. So what I'm planning is, now let's try to summarize whatever the advantage I talk to you guys and discuss on these points. What are these advantages? See, one advantage we talk of when we talk of laser additive manufacturing, the very basic concept of additive manufacturing we always call complexity for free. See what is happening if you take a very complex shape, if you slice into 2D, so every 2D slice becomes a very simple structure. For example, if you make a cone, and if you slice it, it is simple, circle one over another with the reducing diameter. So that is very simple. So this thing is there, and if you extrapolate this to a very complex product and slice and see, you will find the complexity is for free. The second aspect is, in this case, the simplification of manufacturing. If you talk about conventional machining or manufacturing, you need to have very tight, part fixturing will be a different, because there is a lot of cutting forces and so many things are coming on it. So you have to have a different. But in case of laser dye manufacturing, we are using non-contact tools, so things are simple and better. Mass customization is possible. If you see in last 1 century or maybe 1.5 century, the whole engineering started from customized product. See what happened earlier. We have fitters. They were, fitting the job as per the requirement, and that was thing when first or second cars were made. Slowly they started moving toward the standardization of the product. They came with the different standards, metric standards and ISO standards for the components, and all these things were tried out. Even different nuts and screws were tried out, and all these things are standardized. So what happened from customized, we moved to a mass production level by standardization. Now we are going one step ahead. We are taking, mass word from the mass production and customization from the customized product. So we are matching these two, and now we are going for a mass customization because the customer wants everything differently for himself, and it's possible to accommodate in laser dye manufacturing these aspects. Another aspect very important and good, we can think of making integrated components. See what is happening. See, you have a component, you want a sensor inside the material. It is possible to embed it, which is not possible by conventional process. So this is making the thing very much different and making the thing into different aspect. Now let's talk of the material design freedom. The next is material design freedom. Here what we can do is we focus all our studies onto feature based design and manufacturing. What I want to say is you are focusing on the feature rather than the material. So therefore it is providing you a material design freedom. See what happens is, if you are making a component, for example, this component, let's see, in this component, if you want these surfaces to be highly electrical conductive, you can think of having some copper over here. And if these core you want to be strong enough, then you can have stainless steel over here. So that sort of freedom is there, which was not possible earlier. So this is given by the laser dye manufacturing. Another aspect is it is providing you logistic freedom. What is logistic freedom? In logistic freedom, we have a model, we have a component. We can send these models and all the electronic data across the globe, or consult the people. We can collaborate with the different people across the globe and come up with a design. So that sort of availability is there, which was not possible earlier. So talking of the machine and procedures are compliant. This is making the thing altogether different. There was a logistic freedom. In case of laser dye manufacturing, we are using metal or wire into shapeless form, and we are depositing the material as per their requirement, and it is leading to reduce wastage. Reduce wastage means the technology becomes very much green technology. So this is again the aspect. So if we talk of the advantage of laser dye manufacturing, these are the 7 prominent advantages this process has, and making the thing altogether different across this. Now if we talk of the classification of process, the laser dye manufacturing can be classified into 2 different process. One is called powder bed fusion, another is called directed energy deposition. See, you might have heard in classification additive manufacturing, all the process can be classified into 7 classes. And among these two, in these 7 classes, these are the 2 classes. One is called powder bed fusion, another called is directed energy deposition. These are there. Now, if you talk of the powder bed fusion, in this there are 2 processes. One is called laser sintering, and is called laser melting. In laser sintering, what is happening? We are in powder bed fusion. What we do is we simply spread a thin layer of the powder. After that, we use a laser to scan and melt. If melting is 100% of the powder materials, then it is melting. And if it is only surface melting and the particles are joined together, then it is laser sintering. So this is the basic difference, and it is tried. So now let's go to another class, which is called directed energy deposition. In this process, you can use either wire as a raw material or powder as a raw material. When it is used as powder as a material, it is called powder feeding. And when it is wire as a raw material, as a input material, then it is called wire feeding material. So this is direct energy deposition. Just to further explain you what is direct energy depositions, what are we doing is we are getting directed energy, means we are directing energy to a point, and then we are depositing material to give the shape. So this is the logic and how the nomenclature has come. So with this, we go to the next slide. You see, you will enjoy. These are the scenes and scenarios with this particular slide is presenting what we have developed at RRCAT. See, in RRCAT, we have developed directed energy deposition machine as well as powder bed fusion machines. Both machines are working satisfactorily and very nicely. So when I'm showing you the clips of these machines, you see in directed energy deposition machine, we have powder coming and spreading and material is taking place, and powder bed fusion, it's spreading the powder and then going. That is if you compare what is the advantage and disadvantage of this process, you'll find that directed energy deposition can be very good for the functional graded structures, multi-material components, near net shaping components, and complex geometries. On the other way, powder bed fusion system scores point in case of unlimited complexities as compared to directed energy depositions. In this, the deposition speeds are very fast, therefore it resulting in a fine microstructure. So that is another thing. It is very good process for making lightweight structures. And if you talk of the thin features in a fabricated geometry, then laser manufacturing definitely scores a lot. That is the thing which is happening. Now let's go to another aspect of it. When we talk of this technology, there is always a question: what will be the global status of this technology? So what is happening when you see talk of the global scenario? Today we always talk in terms of technology readiness level. And if you see the what is the scenario is there for metal additive manufacturing globally. So if you see from the TRL on 1 to 10, you'll find this is the status. In case of aviation and automobile, we are at the TRL 5 and 6. And in case of tooling, space and drones, we are at 7, 8. And in case of dental, medical instrumentation and other stuff, we are at number 10. So this is our today's scenario. And if you talk at what is happening in Indian scenario, who is doing what, you'll find that most of the industries are working and focusing on the blasting machines. And now some leading institutions are R&D for the laser additive manufacturing. So this is the scenario. And who are having metal additive manufacturing machines in the India? So RRCAT, CMTI, Bangalore, ARCI Hyderabad, DMRL Hyderabad, GTRE Bangalore, IIT Kharagpur, IIT Bombay, IIT Kanpur, IIT Palakkad, CGCRI Kolkata, IGTR. These are the people who are having metal additive manufacturing machines. There are some private players also, for example, Wipro, Honeywell, Incredible, Dental Care, GE, Objectify. So they also are having a metal. So about this machine are developed by who are developing LAM machine in the country. So we have RRCAT, we have developed both the machines, directed energy deposition as a powder bed fusion machine. CMTI is working on development of powder bed fusion. CMRE is developed the DED machines. IIT Bombay, IIT Kharagpur, PSG Coimbatore, and Intact. So these people are who are the player and leading the development of laser additive manufacturing in the country. Now, when we talk of the global scenario, so we started from a globe, we came to India. Now let's come down to LAM at RRCAT. I already told what are we doing at ALAM. So let's say a quick brief about what ALAM is doing. What are we doing in laser additive manufacturing? See, in laser additive manufacturing, we are starting from the system design and development. We go for the material processing. We are doing the material testing. We are also doing the qualification and validation, and we are working on multi-physics modeling aspects. So this is a whole regime that we are working on it. And if you see how the things are being done, these things are working at the junction of advanced design method, manufacturing and material processing techniques, and material science. So if the input from all the threes are coming, and we are working on all these 5 domains. So this is the today, and we are working on the different aspects so that things can be brought to a different level and different aspect. This is a machine that we developed at RRCAT, indigenously developed at RRCAT. This is basically 2 kilowatt fiber laser based directed energy deposition machine having, you see, this is the, we have 2 kilowatt fiber laser. We have an operator console with the Siemens 840D controller. Then we have 5-axis manipulator and dual state powder feeder. So this whole machine is developed by us, and we have our own architecture so that things can be done. And what I want to emphasize here, if you buy this machine from a foreign source, this would be costing in the range of maybe 5 to 7 crores. Now, if you develop this machine, whatever we built here at RRCAT, we hardly spend 2.1 to say 2.5 crores. So what I'm saying, the cost of the machine that is built and imported by other people, and if we start developing these machines in the country, probably we'll be able to provide the things in a very, very low cost, maybe 3 or less what we are importing today. So this is the general specification of the machine. It has got feed rate from 2 to 20 gram per minute, wire feeding 2 to 20 gram per minute. 10D controller. Working volume is 250 by 250 by 250 millimeter cube. And this is having a glow box in which the purity 30 ppm of oxygen, 30 ppm of moisture can be achieved without any problem. This is another machine that we have at RRCAT. This machine is basically on powder bed fusion based methodology. It is having a 500 watt fiber laser, and it's scrap everything built, and even GUI is developed by us. So this machine is working fantastically. And again, it is working for the similar volume. And if you talk about the cost of this machine as compared to the imported machine will be costing you from 3 crore to 5 crore. The machine that we have developed is, we spent hardly 70 to 90 lakhs. So this is the price regime. So here the price can come down to 3 to 5 times of these machines are developed indigenously. So we are further working on a model, trying to bring the things into this so that we can provide a really very good solution to industries, specifically industry solution, specifically to the academic institutes, those who want to join this. And we are working on the design of this aspect, and this would be really very nice if we can have some machine in a very attractive price with all possible feature which is required for a education institute to move on. This is a quick comparison of directed energy deposition as well as powder bed fusion process. You see the feedstock which is used in case of DEDs in the form of powder and wire. Here it is only powder. What I want to highlight in this table is directed energy deposition is very good for multi-material deposition. Powder bed fusion is difficult. Now machines are coming up, different methodologies are being tried out, but still it is difficult. If you talk of repair of this, yes, DD scores very good point in case of powder bed fusion. It can be done, but again there are issues. If you talk of the laser power, it is always more than 1 kilowatt in case of DED and 200 watt to 1 kilowatt for powder bed fusion systems. And if you talk of surface finish, these are the numbers. And these are the qualities, and if you talk about the complexities, these are the status. So this presents a quick comparison of both the machines which is being used as a technology not at RRCAT but also across the globe. So now I'll be talking to you guys about more of what are the process we have developed, what are the different things we tried, and how the things are being considered in this way. Now, if you talk of the process part of it, in laser manufacturing, whole process can be classified into 4 basic parameters: laser related, scans related, powder related, and so these are we will be taking all the other parts in the subsequent. I'm not doing a very much stuff. See what is happening if you talk of the laser. And another parameter which is very important is the scan speed. Now these are the 2 parameters that we are talking of, laser and the scan speed. Now what happens is, if your laser power is very high and scan speed is very small, it results in the Q hooling. When your material is too much melted and some cavity like this is formed, which is not required, because you should put the energy really required to join the material, not a lot of energy. On the other hand, if the laser power is very less or scan speed is very high, you are hardly able to join the material properly. So there would be a lack of fusion porosity will be available. So this is the another scenario. So what happens is, in general, you have to optimize these 2. So when you start optimizing, then you see there is a called balling effect. So you have a some ball formation like this. then you can go like this, or you can those. And further, if you go, you can have a very regular and continuous track formed and that particular parameter. What I want to highlight here is these parameters are different for different material, and one has to really focus very smartly on this and select, identify a real window to work on these areas. Another aspect which is important for is, though it looks that this balling effect is very bad, but these are highly reproducible, and this can be exploited to make porous structures. So we'll come to subsequent slides, and in subsequent slides we'll be discussing further. But what you have to keep in your mind here is that here this particular balling effect can be used to make porous structures. Now another aspect is, if you want, if you make a track, you just take a powder and make a line. Let it be a powder bed fusion, or it can be a directed energy deposition, and you cut a section of it. Then that track has got W as the width and H as the height. Now, if you talk of these parameters, and this is a very crucial parameter for anything to happen. See what is happening if the aspect ratio is more than 5. Somewhere here you get a very solid deposition, or if it is less than 5, maybe 3.5 or so, you will get Tora caves. This is very thing which is happening. And what I want to say is, when you have such a reproducible inter-run porosities, you can think of depositing a porous structure. So that is again aspect. So what I said though people said the porous structures are difficult, but there are ways you can have a very good and controlled porosity using the balling effect or using the so these are the things which are considered and made differently, and one has to say. Another important aspect that I would like to discuss is about casting pattern. See, when you deposit, say, rectangle, and you can fill these rectangle block in different ways. Like when we were young, we were small, we used to fill the rectangle with a different way when we are doing the coloring or painting. But here we are dealing with the metals. And when we are dealing with the metals, every different rastering or scanning pattern leads to different thermal stresses and different thermal distortion. So I'm going to present you very nice case in subsequent slides, and then you will love to see it. See the first side, if you see the left top corner of it, we are presenting S pattern. See, in this, what is happening? You are starting from here, offsetting it, then coming down like this. You are making and filling the whole area. In another one, you are making a Z pattern. In Z pattern, what are you doing? You are starting here, going up to here with the laser, stopping the laser, coming back to next point, starting and doing it. So that sort of thing is we are doing with the Z pattern. The third one is, you can also think of filling the same area with a spiral in or spiral out. So we are comparing these 4 rastering patterns to have a very good brief to you guys about how the rastering pattern and scanning patterns change the scenario. See, this is the case. In case of S pattern, you are seeing there is a distortion. There is a distortion you are seeing, right? In case of Z pattern, again you are seeing the distortion here, and distortion is like the way we are scanning in this direction. Here also we are scanning direction. The distortion is in direction. When we talk of spiral in, the distortion is always altogether different. If we talk of spiral out, this is the case. So what I want to say is, though it looks obvious and very simple, that things can be resolved very nicely and without any problem, but it doesn't happen. Every rastering pattern brings a different distortion to the product, and one has to consider these as a parameter. And I'm saying the Z pattern gives the distortion in our case because of the similar heating and cooling pattern during whole process. Another way people try to work on to reduce this sort of distortion, to fill the area with a mandier. What you are doing is you are depositing here in this direction. After that, you are rotating whole geometry by 67 degree and depositing like this. So when you're every layer, you are rotating your rastering pattern by 67 degree, which is called mandier approach, and this is very nice and somehow balancing the effect of distortion and deformation, the effect of that. Another way is having a stripe deposition. You can have, when last surface, just go on deposit like this. See, particular stripe is important because if you have a very surface, for example, you plate of say 300 millimeter by 300 millimeter, by the time you start, you go to that and come back, the heating effect will not be there. So it's better you make a small stripes and then go on doing it. That sort of thing people are trying. People are also trying to have chessboards. You can have a small sphere made and then rotated by 67 degrees. So that sort of thing people are trying. And all these things, all these efforts are to reduce the effect of scanning strategies or rusting strategies for the components. Another point that I'm going to take this and discuss with you is about the design consideration of laser additive manufacturing, what we learn in these years. If you talk of the feature size, we talk of the surface finish, we talk of the part orientation and supports, if you talk of the lateral holes, if you talk of the overhangs and residual stresses and distortion. So you have to have some considerations for deposition. For example, one of the prominent part we talk of the feature size. In feature size, generally, these are beam diameter act as a diameter of a cutting tool in case of conventional manufacturing. Like you cannot have a hole smaller than the diameter of the drill. Similar, you cannot have a feature the size smaller than the size of the laser beam spot. So this is an important point we should take away from here. Beside this, there is a matter of the surface finish which can be controlled by modulating the laser power, by changing the grain size of the powder, by changing the layer thickness. So these are the areas, and typical surface finish that people get is in the range of 5 to 10 micron RA. So this is the value people get it as a surface finish. Now, if you want to make a component, and then you can try a different orientation, because finally, suppose you want to make such a component, you can think of having different orientation and try to find out. Whenever we are doing such things, what we have to consider is we should try to reduce the support structure that we are providing into this, and because what is happening whenever you are providing support structures, you have to spend some time and money to remove this, and the surface quality also get distorted. So you have to really understand and consider these part when we talk of part orientation and supports. Similarly, if you want to make a lateral structures, so the diameter of the hole can be 0.4 millimeter, 6 millimeter, or 10 millimeter. Whenever you are crossing the diameter of 10 millimeter, you need to have supporting structures. Some supporting structures, otherwise this fellow will not stand there in case of the metal. Now, whenever these numbers, how to remove these support structure during the finishing operation, it is again an issue. So we have to spend your designing this. Another aspect is the overhang structures. When you talk of the making a track on a solid block, then you have a very good heat flow. You like this. When you have structures, either you will not have material, as in case of DED, or you have powder material sitting over here. In case of powder bed fusion, in both the cases, the heat flow will be much lower than what we are having here. So in this case, thumb rule is you should try to avoid any angle more than 45 degrees, and 30 degrees is very good. So that sort of thing people think and try to it. And whenever you have a geometry in which these things are not easy to remove on or very difficult to go at, then what we do is we need to come up with some support structure to make the things in different way. Another aspect is we are melting and depositing material in different form and different aspect. So whenever the material is melted, it expands naturally. And the thing is, the moment it becomes liquid state, the old stresses goes back, and then after that the contraction starts. So this lead to residual stresses in the material, and different hatching patterns result to different residual stresses. And what we have to understand here, if any point of time local residual stress is more than the ultimate tensile strength of the material is likely to have cracks. So we have to take care while considering the design. And now I'm going to present the recent work that we have done at our CAT, and we'll show you, we'll showcase how changing the whole scenario. We are working with many academic institutes and R&D labs, all big names in case of national labs are with, including Institute of Plasma Research, ARC Hyderabad, Vikram Sarabhai Space Center, BRC, IGCAR. And in terms of academic institutes, we are collaborating with IIT Indore, IIT Bombay, IIT Kanpur, IIT Roorkee, IIT Palakkad, IIT Guwahati. And if you see the NITs, there is also a big list. I'm showing you some of them. We have IIT Warangal, NIT Warangal, then NIT Karnataka Surathkal, and we are also collaborating with NIT Ahmedabad. Then we have IIT Kanchipuram, we are working, IIIT Kanchipuram, we are working with. So many institutes are working with us, and we are trying to give it this, considering this understanding that it is not possible to have a dent impact in metal additive manufacturing technologies. So we are collaborating this. Whenever this comes and you have and about the non-disclosure part, we'll not be sharing whatever ideas you have. Then we'll see how other institutes who are put up with us, where your proposal stands, or we don't want redundancy in the work. Then normally, if there's no redundancy, we accept as it is. And if there is redundancy, I may suggest you what are the changes you should have in your project, so that it can be taken by RRCAT and we can extend the first support in terms of the processing. So that sort of thing we do it. And once these things are done, we can plan and work on jointly and collaborative. Idea is to whatever the facility built at RRCAT should also go to every academic institute, and students and faculty working in different domain of the additive manufacturing should take the advantage of this. Now, when I talk so much and discuss many things, let me give you the example, some of the things. This is the work we did for Indira Gandhi Center for Atomic Research, our home work. You see, they wanted bushes, something like this. These bushes are pretty good and used in control rod drive mechanisms and feed rod drive mechanisms. So many places. And the basic reason for using these bushes are to avoid galling. What happens is, in the reactor, nuclear reactors, when materials are exposed to high temperature and pressure, and they stay for very long time, then they have a tendency to weld themselves, and this effect is a problematic in galling. And when you want to use it, so they may not be performing the operations. So to come out of these issues, the people use some anti-galling materials, and Delero 50 is one of the material like this which is used. And the problem with this material is a very hard material. For example, the hardness in the range of 750 to 850. That sort of VHN is the hardness. So you cannot simply use it. And conventionally, what our people were doing earlier, they were making a block like this. They were making block like this. They used to do GTAW. They used to deploy GTAW process to deposit material, and they used to machine in and out surfaces so that things can be shaped into this form. But what was happening in this process? When you are doing this, you have to remove all the dilution layer that ever you deposited. So they have to remove a lot of material in that case. What we did is we just simply made a helical upward motion. This and this change the whole scenario. And the scenario changed so much. It was taking 45 days to make the bushes, done in 72 hours. Another pretty beautiful example is making this mesh type spacers. You see, it has got 37 holes. The wall thickness is 0.4 millimeters, and you see you have a diamond shapes, triangular shapes, and circle shape. And what the conventional way of making this was, they used to take a block, they used to do EDM wire cut, and in doing this process, because here when we talk of wall thickness of 0.4 millimeter, the deviation they want is 50 micron. So wire cut was the solution. So they were using EDM wire cut for making these blocks, and it used to take 2 to 3 weeks to make 5 to 7. And when we deployed our powder bed fusion machine to build these components, we could deposit each mesh type spaces in 2.5 hours. Such 42 spaces were built by us, and it is sent to our sister concern, BARC, Baba Atomic Research Centers, and it is being tested over there for the work. This is one of the beautiful example. Another example is making honeycomb shaped orifice grid plates. You see here, this looks very simple. The diameter is about 100 millimeter, 92 point something is the right one value. So this is the diameter of the tube. Then you have so many boss and then ribs, and this makes things very complex in the applications. So many processes were tried out. For example, they tried conventional casting, investment casting, or even GTAW were tried. Small pieces were pushed and joined together. So, but again, things were not to the level they wanted. So some of these components are built, and they are found to be within the tolerance zone, and now this is being tested for sodium wet. Another nice example is making of compact heat exchangers. So you see, this is heat exchangers These are particularly being used for advanced generation 4 nuclear reactors and solar thermal energy generation. And what is the beauty of these heat exchangers? These heat exchangers are having very small channels. The size of the channel I'm talking of is about 2 millimeter wide and say 3.5 millimeter high. So it's such a small channel. And these need not to be straight. You can have any wavy shape on this to increase the heat transfer. So that sort of thing is that. So what we do is we deposit it layer by layer, and these things are a component for the future, and will be used for in supercritical CO2 Breton cycle, thermal generations, and what I want to say is these heat exchangers are conventionally made by followed by called as that is the thing. They do it diffusion bond. So what they do is they do the acid etching to make the channels, and after that they send all the they stack all the plates and take it for the diffusion bonding in the furnace. So that is the way it's done. And the cost of these heat exchangers by conventional process cost in the terms of 70 to 80 lakhs rupees. And we built this company is maybe spending by maybe 7 to 8 lakhs, and that is the thing we are talking of by deploying this. And now these modules are ready with our, we are going for the next level of testing. Another fundamental and very nice study we did is with the deposition of silicon carbide layer on a thin zircaloy tube. That tube thickness is 0.6 millimeter, and you have to deposit 0.2 millimeter silicon carbide layer. We tried and successfully did it, and now this particular work is very important because we are developing this for taking care of post Fukushima challenges generated within the reactor technology, specifically in case of high temperature oxidation and heterogenation. So these are the things we are trying and built it. We are also doing some basic research. We are trying to develop deposit copper, trying to understand how things are there. And what we found is the copper is very interesting because we got very cohesive, uniform cellular microstructure, which is not possible. And this is done already published in one of the work. Another thing is we also try to build composites of SS and tungsten carbide. This we did with the NIT Warangal. So that is also pretty good work, and how the hardness of stainless steel can be further increased without compromising on the metal card. That's we did it. Another application we built it for Institute of Plasma Research with IIT Kanpur. In this particular work, what we have to do is we have to deposit copper. We have to deposit molybdenum on copper. And this particular work is going to be part of ITER project, International Thermonuclear Experimental Reactor, which is being built at France. And what they want is these copper to extract a lot of heat, and molybdenum is required because this is going to phase the plasma, and this is the first layer. So that sort of thing we will run, and we tried and developed the process. Now we are going for making the component at the second level. I was talking to you guys, and I also briefed to you about porosity and porous structures and different aspect of it. Can you think of making a porous structure which is 0% porous here and the 60% porous here? This is possible because in additive manufacturing and laser additive manufacturing, we are using pattern pencil, and writing 3D shapes. So it is possible. And when I'm talking of the porous structures, many times we have been taught that porosity is very bad in the material. It is not true. The reality is uncontrolled porosity is bad. If a porosity is under control, you know how to use it. Probably porosity can be a beautiful thing for us to use and apply it. So greater porous structures, porosity at defined location, porosity at the desired size, achieving a different sort of thing is possible, and it can be done. I'm also presenting you many specialized components built by us. For example, here with honeycomb core, this is built in 4.5 hours. Diameter is 100 millimeter, thickness is 25 millimeter. Spacer you already saw. We also made one prototype hip implant and impeller. So all these things are built by us using our Indian machines built at RRCAD, using the raw material procured from indigenous sources and sources from here, and this is from the open market. So that sort of thing and technology we have built and developed at RRCAD. And after this, I'll be talking to you what are the technological challenges we have as India or as a community of laser additive manufacturing people. See, we have to understand the laser additive manufacturing has got a lot of issues in terms of the cost. because the input cost is very high, the primary investment is very high, people have a lot of money. So production cost is very high in case of laser manufacturing. It is limiting it to the field. But what I am seeing is in time to come, there will be more manufacturers, there would be more machines available on some better technology. The development cost and patent sort of things will also be removed. So once these things go, these patents are expired and all these things happens, then the cost will definitely come down and it will lead to lower production cost. Today, there is a challenge to process materials, and really, I told you, because of the distortion and directional deposition of the microstructures, we have a lot of issues in terms of the compression, tension, and shear. So every time we have to identify, work on, systematically define the way so that a better and good things can be tried out. To resolve the issues created during the process, we have to go for a post-processing. People are trying to develop different methodology for it, but again, this is a limitation. We have to see it. We have to work on it. Today, you cannot build. There is a limitation posed by the like I told you, both of our machines are 250 by 250 by 250. We have larger volume machines, and which will be available soon. With the stair-stepping effect. So these are limitations that today we have as far as laser manufacturing concerned. If you talk about a lot of opportunities for us, from machine to software development to process development and control, from material feedstock development to design for LM, modeling, simulation, accreditation testing. So a lot of things are there, even in the quality control and assurance aspect, developing and bringing a new application into it. Not only all these, importantly, education and training. So these are the 9 domains we need to work on and bring the things in different. Let's see what other things can be done in each domain. Let's talk about the first, machine and software development. We know that there is a huge capital investment and limited resources. We need to come with an innovation so that these things can be brought down and it is available for a common man to work in nicely. On the other way, if we talk of the process development and control, people are trying to do a lot of things into this. People also focusing on the specific applications, especially in aerospace and specific applications, space applications. But still there is issues with the reproducibility. So what we have to do is we have to come up with a very rugged process development and control aspect so that we can contribute to laser die manufacturing in another way. Presently, a lot of material which are developed for other applications, for example, for the plasma deposition or from oxyfuel depositions, these are being used here as a feedstock material for laser die manufacturing. Now, issue is all these materials are developed for those process, keeping some specific applications in the mind. As a people working in the process, we can always think of tweaking these composition so that we can ensure the performance of the material the way we want. So that sort of thing is possible, and there is opportunity for us to work on. We can also think of bringing in new alloys and AM pertaining to the specific application, so we can give a lot of thrust and push into different areas. There is opportunity for us to draw line or different rules and thumb rules and design rules, so that this whole technology, which is today, I'll say that it is an art. It's not a science and technology. Today, we think how the things have to be done. See, something similar. If we talk of finite element method, it's very simple and very easy to start it. But finally, again, FEM is art. How to reduce the resources, how to work on different. Something similar is in case of LAM today. We have to move ahead, define the methodology, come up with the rules, so that this LAM is a viable and very good process. And in this the whole scenario, what we have to do is we have to unlearn the process we have underwent. We wish for a substantive and formative process applications. We have to unlearn all these aspects, and then after that, we have to come up with a different format of developing the process, so that we are getting rid of this replacing approach. See, LAM is not, is not a very good solution. If you simply say conventionally this is made, they say let's try to do this. No, you have to pour a lot of design thinking into it, come up with some better solution. You have to reduce the number of parts. You have to also reduce and the size. And because here the complexity is being challenged in conventional process, here it's a simple. So many things which you need to work on and come up with the design through the rules. We have to work on the modeling and simulation aspect. We all know that analytic models are very good and fast, but not suitable for complex structures. On the other way, numerical solutions are taking a lot of time. So we have to come with nomograms and machine learning process and different aspect of, or maybe hybrid of analytic and numerical model, or maybe some stuff, so that we can give a better solution in terms of modeling and simulation, and which will provide us a very good, nice and testing of them. We also have to work on the characterization testing. More sophisticated tool has to be deployed, like micro-CT machines, and simulated load testing setups has to be thought of, come up with solutions. There is a lot of scope for us to work on, and this is it. When I talk of the quality control and the assurance aspect, there is a rule to think of it, what should be the design code, how SME sections and others can be used. See, today we talk of strength of the material, other thing, we simply are making a pressure vessel, or vacuum vessel, we simply say we can use ASME section 8. Similarly, if we talk of the reactors, we talk of section 3. So, or if we talk of the vending, we have section 9. So what I'm saying, there is a need to have some standard like this, where people can, think of and blindly follow it and take that advantage. So there is a need to develop and contribute into this, and this is the opportunity. There is also a need to have a certifying agencies and guidelines, so that the material which is built by the conventional process or by laser additive manufacturing process is certified to be comparable or good for a conventional or particular applications. So there is a need to work on these areas. We need to work on entry of new domains, capability demonstration, dissimilar material joining. These are the area where application development people have to work on. When we talk of all these 8 domains, definitely there is a scope to work on the development of curriculum. There is a need to have faculty development. A lot of faculty development program is being taught in the country today. And these things are changing a lot of scenarios. Basic aspiration in the crowd. So that sort of things which is important for all of us to work on and make the things and things happen better. With this, I will jump to the summary slide. The summary slide is like this. You all know that laser additive manufacturing is a novel method capable of providing new manufacturing. There is a distant lead at the international level. India is galloping for the adoption. RRCAT has taken leading role from machine development to the process modeling. We are collaborating with other national labs and academic institutes, and supporting them in a big way so that they can come up. And I want to tell it, we are not charging any money from academic institutes for processing their samples and doing it. So that's sort of advantage we are taking. What is required? We need to come with the more innovations, so that what are the limitations are there in terms of the process and the material condition that can be removed. We can go for a better way. And there is a need to tackle all the 9 domains that I have discussed for the successful deployment of this technology in bigger way. With this, I stop. Thank you very much and patience hearing to me.
Thank you, Dr.
Yeah.
If there are any query, participants can ask. I'm allowing them to unmute. Participant, you can unmute yourself and you can ask questions if you want to ask.
Hello.
Yeah.
Yes, sir, I am Ajay from NIT Patna.
Yeah.
Sir, I have one question. Sir, why 67-degree rotation angle is taken after every layer?
Yeah, this is very nice and curiosity driven questions. See, what you have to do is you see the way melt pool forms. Okay. And in melt pool, you'll find that there is an angle of somewhere between 60 to 80 degree falling as the laser beam moves during the scan. So tailing edge makes angle of 60 to 80. Now you can have any angle between 60 to 80, it will help you. But issue and the dominance of 67 degrees, because 67 number is a prime number, number one. So selecting a prime number means you will take a very large number of layers to come to return to the same location. That is one aspect. And second aspect is this is falling between 60 to 80. So these are the 2 major criteria. And if you really want to see this is published in one of our recent paper by Jinup, why this angle has to be selected. Jinup is one of my PhD students. You can go through this and then you can find out more details. I know you can write to me. I can select and select a portion I can tell you. And these are the 2 major issues, reason for doing that. Yeah.
Okay, sir. Thank you, sir.